Welcome to the Communication Hardware in Robotics course. In this course, we will shift focus to the hardware side of communication robotics. We will start with an introduction to the key hardware components that make communication possible. Then, we will look at microcontrollers and microprocessors. Next, we will cover actuator control and feedback mechanisms. Finally, we will see how all of this comes together in the integration of communication hardware within robotic systems. So, this part is all about understanding the physical building blocks that make communication in robotics work. In robotics, communication hardware components allow the different parts of a system to talk to each other and work together. Some of the key components include microcontrollers and processors, which act as the brain of the system, and communication modules that handle data transfer. We also have network interfaces to link systems and sensors and actuators that provide input and execute movement. On top of that, there are human-robot interaction interfaces like control panels. Finally, communication hubs and gateways help integrate multiple devices into one network. Microcontrollers, like the Arduino Uno, are compact devices that combine processing memory and input-output pins. They are excellent for handling control tasks such as reading sensors and driving actuators, often with built-in communication interfaces. This makes it suitable for complex tasks such as vision processing, data handling, and network communication. Together, microcontrollers and microprocessors form the backbone of robotic systems, one handling low-level control and the other managing higher-level processing and connectivity. Actuators are the components that give robots their ability to move and interact with the physical world. They include motors, servos, hydraulic cylinders, and pneumatic actuators. To manage these devices, we use actuator controllers. Motor controllers regulate speed and direction, while servo controllers handle precise positioning. For stepper motors, step-gear controllers send pulses to move in exact steps. And for heavy-duty systems, hydraulic controllers manage the flow of pressurized fluid to control forceful movements. In short, actuator controllers are the bridge between the robot's control system and its physical actions, turning digital commands into real motion. Motor and servo controllers are essential for regulating how robots move. One common technique is PWM, which adjusts the motor speed by varying the width of the electrical pulses. For communication, controllers often use serial protocols like UART, SPI, or I2C. These allow microcontrollers or computers to send commands and receive feedback from the motor system. In larger robotic systems, CAN bus is very popular. It's a robust communication network that enables multiple motor controllers to talk in real time. It uses two digital pins. One pin sends step pulses to move the motor in small increments, while the other sets the direction of rotation. This makes stepper motors very precise, perfect for applications like 3D printers or CNC machines. Another key feature is the GPIO, or General Purpose Input-Output pins, which are found on boards like the Raspberry Pi. These pins can program to send or receive signals, making them very flexible for motor control and integration with other sensors. Feedback mechanisms are what allow robots to know how well they're performing and to adjust their movements in real time. They provide information about the actual state of actuators and the system. For example, encoders measure position and speed, while resolvers and potentiometers give angular position data. Pressure sensors and force torque sensors help robots sense the physical forces they are applying, which is vital in tasks like gripping. And accelerometers and gyroscopes measure motions and orientation, keeping robots balanced and stable. With these signals, robots can correct errors, achieve precise control, and maintain the desired behavior. Encoders are sensors that measure the rotational position, velocity, or displacement of motors and joints, making them critical for precision in robotics. There are two main types: incremental encoders, which output pulses as the shaft rotates and are great for speed and direction, and absolute encoders, which provide a unique code for its shaft position, perfect for applications where the robot must always know its exact position. For communication, encoders use different interfaces. Digital AB channels are common incremental types. SSI or BISS are often used in high precision and high resolution absolute encoders, while I2C and SPI are found in important modern device encoders for embedded systems. In short, encoders give robots accurate motion feedback, which is essential for tasks that demand precision and repeatability. Resolvers are analog position sensors that are highly valued in industrial robotics because they perform reliably in harsh environments like high temperatures, dust, or vibrations. They work by generating sinusoidal signals that represent the angular position of a shaft. However, since modern controllers use digital signals, a resolver to digital converter or RDC is required to translate this data. Once converted, the signals can be integrated through communication methods such as SPI or parallel buses. Resolvers are often chosen when durability and reliability matter more than resolution, making them ideal for heavy-duty robotic systems in factories or aerospace. Accelerometers and gyroscopes, often combined into IMU, are crucially for providing data about a robot's orientation, acceleration, and angular velocity. They typically communicate over I2C, SPI, or UART, and can output different types of data such as raw sensor values, Euler angles, or even quaternions for more complex motion tracking. In more advanced systems, IMUs are combined with magnetometers, forming what's known as a 9-DOF IMU, which gives highly accurate positioning and movement information. These sensors are widely used in robotics for balance, navigation, and motion control, making them essential for drones, mobile robots, and humanoid systems. This is the end of the course. Thank you for watching.